It's great honor to have the opportunity to participate in this IPSN and show our work on behalf of our team. Our job is to design a anti-interference cross-technology communication, which provides the possibility of communication and the coexistence of multiple IoT devices. In the recent years, we have witnessed the rapid growth of the Internet of Things, in which a large number of devices are connected for a range of applications, such as smart home, smart city, and so on. These devices are connected different wireless protocols, such as Wi-Fi, Bluetooth, and Zigbee. But this device cannot communicate directly, and will cause coexistence interference. Therefore, there is cross-protocol technology to solve cross-technology interference. The gateway can also solve this problem, but at a higher cost. Compared with the gateway, the CTC has more advantages, and CTC has low cost, low deployment complexity, and low communication traffic, and no additional hardware required. But the biggest problem with CTC is cross-technology interference. At present, there are two major types of CTC. One is the packet level, which uses external characteristics coding and anti-noise. And the bit level CTC operates based on signal simulations. But the packet level is easier to implement than the bigger level, and has the stronger versatility. But the CTC still has the common problems. Its anti-interference ability is weak, and have low communication efficiency and low synchronization efficiency. We propose the following method to address these issues. PRComm is implemented on chemical equipment and is a packet-level CTC, which increases the versatility and improves the communication efficiency. And we use M sequence to decode to improve the anti-interference ability of the packet-level CTC. Dynamic decoding strategy improves communications efficiency. And another limit of the packet-level CTC is interference. For example, the zero symbol be occupied by external interference and it be misjudged, and the one symbol be misjudged as the zero symbol due to the delay mechanism. Therefore, in a complex environment, due to the cross-technology interference, chemical senders cannot send packets on time. And another problem with the packet-level CTC is the insufficient utilization of the packets. And generally, the information sequence will be separated from the synchronization sequence. Decode is completed after synchronization. Separate synchronization and information transmissions filter lead to insufficient utilization of the packets. And this is our system designs. and encoding at the sender, simplifying sequence recovery and decoding at the receiver. And another challenge is how to create sequence features to solve the above problems. And PRComm uses the M sequence to construct the coding sequence. There are auto-correlation and cross-correlation between M sequence. Auto-correlation represents the dependence of the instantaneous value of the signal at two different time points. When the offset is 0, the auto-correlation coefficient is 1, and the cross-correlation indicates the similarity of the two sequences. Therefore, auto-correlations be used for the synchronizations, and the cross-correlations be used for anti-interference decoding. And the ability of the long sequence to resist interference will also become stronger, but it will also greatly reduce the communications efficiency. Therefore, we need to maintain a balance between anti-interference ability and communications efficiency. We're looking for coding sequence of different lengths for the scenario with different interference strengths. And the sequence length is proportional to anti-interference. And when the offset is 0, different length sequence both have the high auto-correlations. But when the 1-bit errors occurs, the long sequence have the high auto-correlations. So, therefore, it's necessary to balance the sequence length and fault tolerance. So, different sequence lengths are selected in different environments. And another challenge is how to create packet characteristics. And how long the data packet used to carry important energy characteristics without consuming too much throughput. And the manned CTI, the recognition rate of the 360 bits reach 18%, while the correct decoding rate of 115-bit packets is only the 15%. So when we only use the symbol once, the packet is easy be damaged by the noise. So in the PRComm, the length of the data packets should not be less than twice the sampling parameters. And the biggest problems in the sequence recovery is the CSMI interference. CSMI is a channel interference avoidance mechanism in chemical equipment. When the channel interference is strong, the data packet transmission of the channel is stopped. Therefore, CSMI will cause delay in the sender packets, forming the illusion of sending 0 packet. There are mainly two results: insight between the original 1 packet and overwriting the original 0 packets. The first is to use transmitter energy characteristics interval characteristics or the M sequence calculations to animate interference. The second is use a composition mechanism to directly remove zero and calculate the cross correlations. If the cross correlation is high, the compositions zero symbols and calculate cross correlations again. And we count the delay caused by the CSMA and the forecast of the frequency interference. The 62% average delay is less than 2 periods at low and mid frequency. The 28% is less than 2 periods at high frequency. So we use the 2 period for symbol dynamic matches. Under the synchronization and decoding, the sequence at the receiver is shifted and convolved to calculate autocorrelations and cross-correlation for synchronization and decoding. And after 2 high autocorrelations, the synchronization is successful. And this is our implementation. We deployed the equipment in the 3 different environments. The sender is a chemical PC with a 5300 network card to send the Wi-Fi packets. The receiver is a chemical Zigbee node that collects RSSI. We also compared the symbol error rate after only related coding and used dynamic synchronization. Dynamic synchronization decoding reduces the simple error rate in the 3 environments by 2 times, 5 times, and 2 times respectively. We also compared the synchronization time of only coding and dynamic synchronization. And dynamic synchronization can shorten the synchronization time to at least 4 times of the original. This is the evaluation, and we compared the encoder in the same experimental environment. Encoder is the packet-level feature decoding CTC, and the amount interference. The accuracy of the 2 CTC is similar, but under the moderate and several interference, encoder doesn't consider the impact of the CSMA, and the accuracy drops sharply over the time. And PRComm restores the sequence dynamically and reduces the delay errors and makes the decoding stable. In the terms of the synchronization strategy, encoder adopts the pre-sequence synchronization method, and the resynchronization time is twice than PRComm and the moderate interference environment, and even 3 times than PRComm and the several interference conditions. Thank you. Thank you for your listening.